All right, hello everybody. I thought we'd go ahead and do notes this way this time. This gives you a really good opportunity to pause and take as much time as you need to write in the blanks, and that way you should be all set. Not everything that you need to write down is underlined, so you will need to pay special attention to your notes as you're going through. But this will give you everything you need to know about Newton. And afterwards, you'll start reviewing for your test, which we will take next class. So yeah, I know you're excited for that. So let's go ahead and get started. We'll be talking about Newton. And the couple of things that we'll be talking about is his first law, his second law, and his third law. Of course, those are very important. But then we're going to talk about his laws of gravitation and how gravity itself works. And we'll talk about how the size of the object affects how much gravity there is and things like that. So I want you to pay special attention to how the gravity acts in space. So the first thing is we need to talk about Galileo, and there's a short little video that I want you to watch that has Galileo's experiments. He actually did experiments before Newton did. He noticed he rolled balls of different masses down inclined planes, and then this allowed him to explain inertia. And without inertia, we wouldn't have Newton's three laws because it's needed to understand those. So we are thankful for Galileo's experiment. So he did more than just the heliocentric thing. Some important laws that relate to astronomy are the laws of gravity that he created, or he discovered, I should say. His three laws of motion explain how and why things move. The law of gravity explains how things are attracted to each other. And things are attracted to each other the way a magnet is attracted to a refrigerator. So if you put a magnet up to a refrigerator, as it gets closer, you're going to start feeling the pull, and then all of a sudden, as you get closer and closer, the pull is stronger and stronger. That's how gravity acts. It also acts, the repelling force is something that you're familiar with if you try to put two magnets together of the same size, but again, you only feel that when they're close together. So that's how gravity is. The closer you get, the more you feel. And then his laws of motion explain why planets are moving slowly. It explains orbits. It explains how objects form, how to get into space, kind of an important one, and how to live and work in space, which again is pretty important nowadays. So this is just an example. The movie Gravity, I don't know if you've seen it yet. You are going to be watching it, so you will have an opportunity to watch this particular thing. I don't think we'll watch the whole thing, but we'll watch a good portion of it. And this is Sandra Bullock. Hopefully everybody knows Sandra Bullock, and she's flying off into space, and she's trying to catch herself because once she starts moving in space, she will move in space forever unless something stops her, which is Newton's first law. So you're probably familiar with it, at least you've heard it before. Basically, an object that's at rest is going to stay at rest. So if something is sitting still, it's going to stay sitting still unless something acts on it and makes it move. So that is how Newton's first law works. And when it moves, it'll always move in a straight line unless it's acted on by another force. So an example is this guy riding his motorcycle. So he's still going and he's still going. His motorcycle stops, but he continues to go, right? He's going to go in a straight line until something acts on him. This one is just for fun. Students, as you're sleeping, you're going to stay sleeping, and as you're working, you're going to stay working, hopefully, usually, unless you're acted upon by another source, which would be wanting to play a video game or wanting to, get up from the room and talk with your friends, that kind of stuff. So that's that. And then this is a bumper sticker that I want. I'm not lazy. I'm just addicted to inertia. So I'm waiting for inertia to push me. So just some funnies. And then hopefully you've seen Lucy hold the football for Charlie Brown. It's the same kind of thing as the guy on the motorcycle. As he runs and he runs and he runs, he misses it. So he throws his leg up in the air. He continues to travel. He doesn't stop until gravity acts on him. So another force acts on him. So Newton's second law is saying that if something acts on, if there's a force and it acts on an object of mass, it's going to make something accelerate. So if you push something, it's going to move. That's basically what Newton's second law is saying. So here, you can see that mass does play a role on, um, on movement. But that's primarily, or I'm sorry, force plays a role. So here, this poor woman is not going to get pushed very far by her daughter. This is a very good example of how Michigan State tackles the Michigan player and stops, forces, kind of accelerates him to the ground. I like that example. It's a really good example. And of course, I don't know why she's wearing heels, but she is, and she's trying to stop the car from running her over, which again, there's an object of mass. It's coming down a hill, it's producing an acceleration, so that's why she needs to stop it. Then there's the third law of motion. So this is another one you're probably really familiar with. For every action, you have an equal and opposite reaction. So if you are pushing forward on, or pushing backwards on the skateboard, you're going to go forward, right? If you are hanging out with your friend in a spacesuit in roller skates, because I know we do that all the time, spacesuits and roller skates, right? So if you're doing that and you push against somebody, you're going to roll backwards. I have one of these in the classroom. This is Newton's cradle. As this one ball hits, the force is going to go through all these little balls, and that ball is going to come forward. So take a look at that in the classroom. So once again, I love this cartoon. I love the two cartoons on here. Here they are, they're in space, they're, working on the spaceship, and they fixed it, yay! And so he jumps and he high fives, but of course that force forces him to go away. So that's bad. This is why I do not teach elementary school, because I would probably do something like this. This is trying to make Newton's cradle work, so this kid is supposed to go hit that one, and these are supposed to go through, and then this kid's supposed to go out. So I'm curious as to whether or not that would actually work, and I really do want to try it, but I don't think I'd keep my job if I did that. Okay, so now we've got Newton's law of gravity. So you've heard the story. He was sitting under an apple tree and an apple fell on his head, and he said, aha, gravity exists. And that's kind of true, but what he did is he noticed that whatever was pulling that apple down to the ground was the same thing that was keeping the moon from flying away from Earth. So that's what he was noticing, is that it held the moon into its orbit. He never said that the apple landed on his head, by the way, but there is documentation. He did say he saw an apple fall, and then he wondered why the moon was being held to the earth. So this is the full moon. He was wondering why the inertia didn't cause the moon to fly off into space. So he realized that a force must be holding it. So he realized three things. He knew there was a force of attraction between the Earth and the moon, and the force had to relate to Earth's mass. So he noticed that. From his third law of motion, he knew that if the Earth was pulling on the moon was pulling on it equally as hard, or it would either move closer or it would move farther away. And then he noticed that, like a magnetic force, the distance between two masses increased, the force of gravity grew weaker. So again, think of the magnets. If you have two magnets attracting to each other, or even one going to the refrigerator, the closer you get, the stronger it feels, and it happens very quickly. It's the same thing with gravity. The closer you get, the stronger the gravity feels, and it moves. It happens very quickly. So let's take a look at how quickly. This is the inverse square law. This is what explains how gravity works, or one version. This is the easy version for you, because let's face it, math is not everybody's strong suit in this class, nor is it in many classes, nor should it be necessarily. So we're all intelligent, we just know different things. So just remember that. Anyways, the force of gravity is equal to 1 over the distance squared. So basically what that's saying is the force of gravity is related to the square of the distance, the inverse square of the distance. So the closer the objects are, here the force is equal to 1. This is the Earth and this is the moon. Let's say the moon now moved a quarter of the way farther. All of a sudden, or I'm sorry, it moved 2 times away farther. So that would be 1 over 2 squared. So now the reaction, the force is only 1/4 of what it was. Same thing down here. If it moves 3 times farther away, it's only going to be 1/9 the force. So it happens very, very quickly, and you can see that in this image as well. This is equal to 1. If they move twice the distance, all of a sudden it's only 1/4 of the feeling of gravity. If it moves 3 times away, it's 1/9 the feeling of gravity. So it changes very, very quickly. So in general, the distance between the Earth and the moon, if they were decreased to 1/2, the force of gravity between the Earth and the moon would increase, so it would be 4 times stronger right now. So that's the opposite. So you have the force of gravity is equal to 1 over the distance. The distance is now 1/2 of what it was. When you put a fraction underneath a 1, you take the number that's at the denominator and you put it up to the numerator, so it's 2 squared, so it'd be 4 times as strong. So that's really, really strong. So in general, what you need to know, because you don't need to memorize the equation, so what you need to know is the closer it gets, the stronger it gets, and it happens very quickly. The farther it gets, the much, much weaker it gets, and that also happens very quickly. And it's related to the distance that the object is from the other object. And that's how the force of gravity works. So this is the actual equation. As you can see, it's a little bit longer. You have the Earth of the mass, and the mass of the Earth, the mass of the moon times G, and G is a constant. And so we've got that F is the force of gravity, and this is true for any 2 objects. So I'll let you guys look at this for a second. Some of you are very mathematically inclined, so if you take a look at this, maybe the equation will make sense to you. So you can pause the video right here if you want to. And if you put it all together, this is the equation that you get. But what this means is, and again, this is what's important, is what it means. It's like Kepler's laws. I just want you to tell me what they mean. I want you to tell me what Newton's gravity means. And here it means that every object in the universe is attracted to every other object in the universe. You are attracted to the center of the Milky Way. The center of the Milky Way is attracted to you. So even though that force of gravity is extraordinarily, like really, really weak, it's still there. It still exists. Yeah, so the black hole in the center of Milky Way, like I just said that, I'm reading the slide all of a sudden. So if the 2 objects that were small, the force of gravity would be weak, like would also be weak. So like you're sitting in front of the computer right now, you're gravitationally attracted to that computer. However, obviously you're not finding yourself getting stuck to it, unless maybe you are. I know some of you get stuck to your phones, force of gravity, I guess. You can use that on me now. It's just gravity. It's making me be on my phone. Yeah, so if the 2 objects are small, even though you're gravitationally attracted to the computer, you're not necessarily feeling it. However, the gravitational force is there. So here's an example. The Earth can still feel this galaxy far, far away. So this is 13.8 billion light years. We can still feel that farthest galaxy away. So what does this mean? What's important about this? It explains why planets orbit stars. It explains why stars orbit the center of their galaxies. It explains why galaxies in the universe are attracted to each other. So it explains why everything moves around everything else. It explains all motion. Now, there is one very big myth, and you hear that there's no gravity in outer space, right? So you don't feel any gravity when you are on the space station. And it's true, you don't feel the gravity, but there is still gravity there. You are still gravitationally attracted to the Earth. It's just that you are so far from the center of the Earth that you are now able to float in space. So that's microgravity exists. In fact, that's what it's actually, excuse me, that's what it's actually called, is microgravity, not gravitylessness. So an example here is if you were to visit Mars, where the gravity is less than it is on Earth, you'd be able to lift 2.5 times what you can lift on Earth. So that would be awesome. And you'd be able to throw a baseball 2.5 times farther, which would be kind of cool. So that's just an example of how gravity affects things of size. So these are things that you need to know. So make sure that you can answer these questions, because these questions will probably appear on your test. So the first one is, what does Newton's first law say about an object in motion and an object at rest? The second one is the relationship between force, mass, and acceleration, which is Newton's second law. And according to Newton's third law, for any action, what happens? Then they want you to be able to compare the gravitational attraction of two objects that are close together to the gravitational attraction of two objects that are far away from each other. How do the sizes of the objects affect the gravitational attraction? And then what are 3 things Newton's laws explain?